Good morning. Hope everyone's doing well today. Wait for a couple more viewers here. While I'm waiting, I'll show off my most recent creation. So I used the metal cutting bandsaw to make this. So if you guys don't know what a bandsaw is, it's basically a vertical saw, and you can kind of push a piece of metal into it, and it'll cut corners and things like that, so you can get kind of these kind of rounded shapes. So I literally just pushed the piece around like this and was able to get this nice curve, and then get this curve and get this curve, and then you just sharpen it. So it goes by really quick. And you can even stack pieces of metal. So you could have like 3 pieces of metal stacked on top of each other and clamped together, and it'll cut through all 3 of them. So you can make 2 or 3 of them that are exactly the same shape. It's pretty cool. See how many I'm at. 15 viewers. The bandsaw blade, yeah, it's so the bandsaw, yeah. So you need to get a special bandsaw basically to cut metal, because most bandsaws are made for wood. So basically, a metal cutting bandsaw, the saw blade, if you have a wood bandsaw, the blade is going really, really, really fast. Okay, so when you cut wood with a saw, the saw is going really, really fast. But different materials are better cut with different speeds. So the metal cutting bandsaw goes really slow, actually. So you can literally see the teeth moving as it goes. It's that slow. So it's just like really high torque on the motor, but slow, and it just kind of goes. And then you use there's like a lubricant cutting oil, and so like when I figure out where I want to cut, I have like a piece of chalk, and so I'll just kind of outline what my idea is in chalk, and then you just kind of drip cutting oil along that, and it lubricates the saw blade, and then it goes a lot faster. Okay. So I think I'm going to go ahead and get started. Welcome, everyone. This is AP Physics 1, February 5th, period 6. All right, so what I wanted to talk about first was last time, just to kind of review the last lesson. It's an important introductory lesson. So last time we introduced the idea of simple harmonic motion. which I will refer to oftentimes as SHM, just because saying simple harmonic motion is kind of a mouthful. And so simple harmonic motion means that your position as a function of time is equal to a cosine of omega t, or sine of omega t, or whatever, it doesn't matter which trig function it is, plus a constant. Okay, so this is the equation of the position as a function of time. If you were to graph that equation, putting position on the vertical axis and time on the horizontal axis, kind of looks like this. Okay, and so what we want to be able to do is we want to be able to go back and forth between the equation form and the graph form. So we want to be able to identify what do each of these how can we identify the amplitude in the graph, for example. So first of all, what we'll notice is that when you do simple harmonic motion, if you're going back and forth and back and forth and back and forth doing simple harmonic motion, because that's what simple harmonic motion is, you're just going back and forth and back and forth and back and forth, there's some kind of a middle point. So we can see that, right about here is the middle point of my back and forth, okay? That middle point can also be seen on the graph, okay? And that middle point is what is meant by C, and it is often called the equilibrium point. Okay, so that's how you determine the equilibrium point. It's the middle of the vibration. All right. Then if we think about the middle of the vibration, the vibration will deviate, the position will deviate a certain distance from the equilibrium point. Okay, so here's the equilibrium point, and we can see that the farthest it goes from the equilibrium point is this far. Okay, and that is called capital A, and that is the amplitude. So the amplitude here is the same as that number right there. So if we look at this graph, we know what C is and we know what A is. Omega is a little bit trickier. So what we would do is we look at this graph, and the time it takes to complete a full vibration is called the period T, capital T. All right. So the period is the time it takes to go back and forth. So it's not, sometimes students are confused. They think the period is the time it takes to go across, but it has to go across and come back to where it started. That is a full period, okay? And the period is related to this constant omega. According to the equation, period is 2 pi over omega. All right. So that was the first thing we talked about was, first of all, what is simple harmonic motion? It's just this boing, boing. You could have vertical simple harmonic motion. So it's going back and forth, which means that the position as a function of time is a sine or a cosine. And then, there are various ways of describing what the details of the simple harmonic motion. Then what we talked about was the equation, that when you see this equation, you know that there is going to be simple harmonic motion. Okay? So I'll call this the fundamental equation of simple harmonic motion. It's whenever you encounter an equation that has that form, you know that simple harmonic motion is going to result. Okay? And that equation is negative omega squared times position minus c times the quantity position minus c equals the acceleration. Okay? So that was last time. This time, what we are going to talk about are some specific examples of SHM systems. Okay? The first system that undergoes simple harmonic motion that we're going to talk about is called the mass spring system. Okay? So what is the mass spring system? Well, you have kind of a you have a floor, you have a wall here, and to this wall you connect a spring. Now what we know is that springs have a natural length, okay? So this is just a relaxed spring, okay? And then on the other end of that spring we attach a mass M. The spring has a stiffness K. All right, and now because this spring is just relaxed, if we attach the mass here, nothing is going to happen. It's just going to stay still, okay? So what that means is that this is the equilibrium position. So I'm going to call this x equals 0, okay? And by the way, the floor is completely frictionless. So it has a coefficient of friction, mu, equal to 0. So let's think about what would happen if we were to take this mass and pull it to the right. Well, that's going to stretch the spring, and when a spring is stretched, it doesn't like being stretched. So it's going to pull the mass to the left. So over here is where x is greater than 0, so we pull that mass and it stretches the spring. What if we took the mass and we pushed it to the left so that x is less than 0, x is negative? That's going to compress the spring, and when a spring is compressed, it doesn't like that, and so it's going to push back to the right. Okay, so we see that whichever way this mass goes, the spring is going to try and pull it back to x equals 0. Okay, so let's go ahead and work out Newton's second law in this case. So Newton's second law is net force equals ma. All right. Now, what is the force that is making this mass go back and forth? Well, that force is the elastic force because it's the spring. Why don't we care about gravity or the normal force? Because gravity and normal force are canceling each other out, and they're acting in the vertical direction, whereas this mass, it's going to undergo simple harmonic motion horizontally, okay? It's just going to slide back and forth along the floor, okay? So the net force is the elastic force, which is kx. So we have kx equals ma. But there's an important point, which is that it's going to be negative kx. Why is that? Well, if we pull the mass so that its position is positive, the force is to the left, which is a negative force. So you can see that the direction of the force and the sign of the position are opposites. Okay, so if we have a positive x, we multiply that positive by a negative to get a negative net force. Okay, so that's why there has to be that negative in there to get the direction of the force correct. If you move this mass to the right and the force was also to the right, it would just keep going to the right. It would just go off the screen. Okay. So now we're going to take this and we are going to divide both sides by m. So we have minus k over m times x equals a. All right. And then I'm just going to rewrite this exact same thing again, but I'm going to make it a little bit more explicit where I'm going with this. So k over m times the quantity x minus 0 equals a. All right. So these two equations are exactly the same because if I take x and I subtract 0, I just get x. Okay, so why did I do that? Well, because what I want to do is I want to compare that with the defining equation of simple harmonic motion. Okay? So the defining equation of simple harmonic motion is minus omega squared times x minus c equals a. Okay? And so what I can see here is that the mass spring system obeys the equation of simple harmonic motion. Okay? Because we can see we have A equals minus a constant times x minus c. So we can just see that there's an exact correspondence between these two, okay? And looking at this correspondence, we see that the equilibrium position is 0. And we see that omega squared is k over m. All right? And this is really what we're getting at because omega is related to the period. So let's do the algebra here and let's actually figure out what is the period of the mass spring system. Taking the square root is going to give us omega equals square root of k over m. Okay? And then the period is 2 pi over omega. So when I do 1 over omega, that means I have to flip this fraction. So it's going to be 2 pi square root of m over k. All right? And so this is the period of the mass spring system. So this is the first of 2 main equations for today. All right, so that is the period of the mass spring system. So I'm just going to rewrite that on the next page since I'm out of space. So the period of the mass spring system is 2 pi square root of m over k. All right, so let's make some observations about this equation. The first observation the first 2 observations I want to make are that this equation makes a lot of sense in terms of our intuition, in terms of what we expect to happen, okay? Now, the thing you have to remember about physics is that physics is an experimental science, and the equations of physics are meant to describe reality. Okay, so if we ever write a physics equation down and it doesn't describe reality, it means we're not understanding something. So let's just double check that this actually does describe reality. So can you imagine for a second a really huge mass on the end of a spring? A really huge mass it's gonna be really difficult to move a really huge mass back and forth. Okay? So it's gonna take a long time for that spring to move a really huge mass back and forth. Okay? So basically what I'm trying to say is the bigger the mass is, the longer the period should be. The more mass you have, the more time it takes to go back and forth. And we can see that that is actually reflected in this equation because m is on the numerator. So as mass increases, so too does the period. Okay? So as mass goes up, the period also goes up as expected. Okay? So that is the first thing. The second thing is, excuse me, we can imagine if we take a mass and we attach it to like a really, really beefy, super stiff spring, a really beefy, super stiff spring is going to be able to pull that mass back and forth in a really short amount of time. Okay? So what we would expect is the stiffer the spring is, the less time it takes to go back and forth. And we can see that stiffness of the spring is in the denominator of the fraction. So as the stiffness goes up, the period goes down, which is as we expect. So that makes perfect sense. All right? However, even at this stage, we get something that's a little bit surprising, okay? One of the things we see is that capital A is nowhere in this equation. Capital A stands for amplitude. Capital A is nowhere in this equation. So what that means is that the period does not depend on the amplitude. And that is an important point. The period does not depend on the amplitude. So what does the amplitude mean? That's how big the swing is. So if you have a big swing that's like versus a little swing, those both take the same amount of time in simple harmonic motion. Okay? Now, why is that? Let's try to understand why it's true. Well, if you have a large amplitude, the amount of distance that you have to cover to go back and forth is greater. If you have a small amplitude, the amount of distance you have to go back and forth is very small. But if you have a large amplitude, you're going to be stretching that spring a lot more. The bigger the amplitude is, the more the spring is stretched. Okay? And if the spring is stretched more, then that means that the elastic force is going to be much greater. And because that force is greater, the mass is going to be able to build up a lot more speed. Okay? So the reason that the period does not depend on the amplitude is that the greater distance resulting from a larger amplitude is compensated by larger speeds. Okay? And it works out in such a way that they exactly compensate for each other, so you get the same period no matter the amplitude. The other thing I wanted to talk about is that you can have a vertical mass spring system. So if we were in class, we would be doing experiments with vertical mass spring systems. Why? Because first of all, you need a metal spring to do this kind of a horizontal mass spring system. And we just have rubber bands in class, so it's really easy to just hang something from a rubber band. And furthermore, it's this is sort of unrealistic because there's no such thing as no friction. So it works a lot better if you have a vertical mass spring system. So what is a vertical mass spring system? You have a ceiling or someone holding something, and you have a spring, and then you have a mass. Okay? And so maybe this is a vertical mass spring system on Earth. Okay? What is the mass spring system going to look like on Jupiter? Well, Jupiter has gravity that is a lot stronger. Okay? So what that's going to do is it's going to have the effect of pulling this mass down further. Okay. So we can see, yeah. So it's basically if you took the same mass spring system and you took it over to Jupiter, it's going to bob up and down, but it's going to bob up and down about a much lower point. Okay? If you took the same mass spring system and you moved it to the moon has a gravity that's about 1/6 what we see on Earth, so you're going to have something like this. Okay? But here's the thing. Vertical mass spring systems have the same period as horizontal mass spring systems. Okay? So even if it's hanging vertically versus moving horizontally, it's the same equation. Still use this equation. Okay? And in particular, this equation does not have gravity in it. It does not have little g in this equation. Okay? So the period doesn't depend on little g. Okay? So all three of these mass spring systems will bob up and down with the same period, no matter the gravity. But what does depend on the period is the equilibrium position, because we can see that this mass spring system is bobbing about this C value. So that's the value for the Earth. This mass spring system, even though it's identical mass and an identical spring, is going to bob about a much lower position because of the increased gravity. And this one is going to bob up and down about a much higher position. But the equilibrium position does depend on G. All right. So we are going to be talking a lot more about the mass spring system next week. But for now, we're going to leave it at that. And we're going to go on to a second system that undergoes simple harmonic motion. And that system is called a simple pendulum. So what is a simple pendulum? A simple pendulum is like you're trying to hypnotize someone. So you have a ceiling or something, and then you have a string that is attached to the ceiling at some point. That string has a length L. And then at the end of the string, you have a mass, M, which is called the pendulum bob, the bob of the pendulum. And then this thing swings back and forth. Okay? That's simple harmonic motion. The amplitude of a simple pendulum is how big is the swing. So big amplitude, small amplitude. Okay? So it's a little bit beyond the scope of this course to derive the equation for the simple pendulum. If you take AP Physics C, we do derive this equation, but I'm not going to here. But I'll just give you the equation because it's useful. So the period of a simple pendulum is 2 pi times square root of L over G, where L is the length of the simple pendulum and G is the acceleration due to gravity. Okay, so this is our second main equation for today. So let's go ahead and make some observations. Okay, first of all, let's just check that this equation makes sense. Okay, first thing we notice is that length is on the numerator. So the longer the pendulum is, the more time it takes to go back and forth. So that's our first observation. As length goes up, the period also goes up. So does that make sense? I would say yes, it absolutely makes sense, as we expect. How many, I would imagine that most of you, if not all of you, have been to Griffith Observatory at some point in your life. And when you walk inside the building at Griffith Observatory, there is a giant simple pendulum there. Okay? Its string goes all the way from the ceiling down, not just to the floor, but below the floor. They have they dug a hole for the pendulum to go all the way down to the floor. So it's a really, really long string. And if you watch that pendulum go back and forth, it takes a huge amount of time. It's just like, okay? So I would argue that just based on the observation of Griffith Observatory, I would say that that is as expected. Okay? That pendulum is called a Foucault pendulum. So that's it's a Frenchman. Foucault pendulum at Griffith Observatory. And so a Foucault pendulum is designed to demonstrate the rotation of the Earth, actually. So a pendulum is going to keep the same plane of rotation, or plane of swinging. You know, you can have a pendulum swinging like this, or you can have a pendulum swinging like this. Okay? It keeps the same plane of swinging. But here's the thing. The Earth is spinning underneath the pendulum. So as the Earth is spinning, the pendulum keeps the same plane, but the Earth spins. Okay? So what would it look like if you were on the Earth? If you're on the Earth and you're not aware of the Earth spinning, it would look like not the Earth is spinning, but the pendulum is actually changing its plane of rotation. And so it, they have some dominoes set up along the rim of the pendulum, and it knocks over them as the plane of the pendulum appears to rotate. But it's not the plane of the pendulum that's changing, it's the Earth that is changing. It's rotating. Okay? So that's called a Foucault pendulum. The second thing is we can see that the acceleration due to gravity is on the denominator. So what that means is that as the acceleration due to gravity goes up, the period is going to go down. And I think that's fairly obvious. If you take a pendulum to into a really strong gravitational field, okay, that gravitational field is going to pull the mass down really quickly, okay? So I would say that this is also as expected. Once again, the period does not depend on the amplitude. Once again. So there is no capital A anywhere in this equation. So if you have a big swing, it takes the same amount of time as a small swing. Okay. So, and it's for the exact same reason as with the mass spring system. If you have a big swing, you have more distance to travel, but you are allowed to build up more speed. Okay? The second observation, which is another one that's not very intuitive, is that the period does not depend on mass. Okay? So whether this is a heavy pendulum bob or a light pendulum bob, it takes the exact same amount of time to go back and forth. Okay? How do I know that? It's because little m doesn't appear anywhere in this equation. But here's the thing. The heavier your pendulum bob is, now if you take a real pendulum and you pull it to one side and you let it go, it's going to swing. And as time goes on, that swing is going to get smaller and smaller and smaller and smaller as air resistance slows it to a stop. Okay? The more massive the pendulum bob is, the longer it's going to swing. It takes the same amount of time per swing, but it's going to do more swings in total before it comes to a stop. Okay? Because more massive things are less susceptible to air resistance. So at Griffith Observatory, that pendulum bob is extremely massive. So it can basically swing all day. They don't need to hire someone to sit there and give the Foucault pendulum a push every now and then because it stops swinging. It's so massive that it can just go all day, and they just do it, set it up once per day. Okay? At least I've never been there while they had someone give it another push. All right. So we're almost done here. I just wanted to talk about some of the uses of a simple pendulum. Okay. So the most obvious use is timekeeping. So for example, a grandfather clock, it's keeping time with that pendulum that goes, okay? And so if you mess around with that pendulum, you're changing the period of the pendulum, which is going to make it not keep time accurately, okay? So yeah, keeping, it's used in timekeeping. Another way you can use this equation is, what if you had the ability to measure the period precisely? So you measure the period precisely. So when I say precisely, I mean very exactly. You say the period is 2.459376 seconds. So you know the period, you know the length, then you're going to be able to solve for the acceleration due to gravity. So basically, you measure the period precisely. You use the equation to solve for gravity. So you can actually measure gravity really accurately using a simple pendulum. And so one of the cool things about this is if you can measure time precisely enough, you can actually see how gravity varies from place to place. Because I know in every homework assignment I give to you guys, I say use G equals 10 meters per second squared. Okay, really it's 9.8 meters per second squared, but we just use 10 just for simplicity. It's a nice round number. But yeah, the more accurate value is 9.8. So you could solve for G, and in fact, this is an experiment we do if we were in person. We would solve for G and show that it is 9.8. But furthermore, if you can measure time even more precisely, okay, you could actually measure variations in gravity from location to location. Because gravity is not exactly constant. It's approximately constant, but it's not exactly constant. It's affected by things like land mass that's around you, okay? If there's a giant mountain next to you, that affects gravity, which affects the period of a simple pendulum. And you can actually detect that if you can measure the period precisely enough. It depends on things like latitude. If you go towards the North Pole versus the equator, this has an effect on gravity. Okay, so you can actually detect that with a simple pendulum if you can measure time accurately enough. Okay, so that is my lesson for today, and I will see you in the Zoom room. Bye for now.